Assalamualaikum warahmatullahi wabarakatuh. My name is Nur Batis Mahadi binti Ahmad Idris and my metric number is 221302403. Today I will be presenting about exercise 1 for Lab 3 where we use linear support vector machine to predict type 2 diabetes risk. We have four objectives which are build a linear SBC model, evaluate with a coefficient matrix, analyze which features are most important, and use the training data from the appendix 2 that given in the lab module. So, for the first objective, we build our prediction model using just two lines of code, which is these two. And the first line is to create the model with C equal to 1.0. We can take C as a flexibility settings, which means this means balance, which not too strict and not too loose. So it's like drawing a line to separate diabetic from non-diabetic patients, but allowing some mistakes. So for the second line, which is this one, is to train the model. We give it 9 to 10 patients records with their features and diagnosis, and the model will learn. When I see these feature patterns, this is usually the outcome like that. And it finds the best dividing line between the two groups. So the question 2 is coefficient matrix evaluation. I mean the second objective. And that objective is in this part, which is this line and this line. So this line is for us to make a predictions on 2 to 3 test patients we didn't train on. And this part is to create the coefficient matrix. Like it's a 2 by 2 table that shows four things. The first one is non-diabetic. This one in the X tick level. Non-diabetic. Where we correctly identified. The second one is the false alarm. We said diabetic, but they are not. Like here, this one. And the third one is the missed case. It's actually diabetics. They are actually the diabetics, but we said no. So this is kind of dangerous. The last one is diabetic patients. We correctly caught. Alright, that's the four confusion matrix that we show. And the result, I will show you the result later. So for the third objective, which features are most important, which medical features are the best prediction. The model gives each feature a weight, like a score showing how important it is. So let me show. The first one is the glucose. The glucose is the champion or the highest weight, means most important. Wait a minute. Okay, here. We can see this is the coefficients coding. The coefficient codings in the step 5 and the coefficient codings in the step 3 is the most important for this part, where we need to analyze which feature is the most important in this practice. So the first one is the glucose. So the first one is the glucose, and the second one is BMI weight. This is the second most important, and its higher body weight increase the diabetes risk, and it is also a well-known medical fact confirmed by our model. And the last ranking, like we can say the age, blood pressure, and the pregnancies is the smaller weights. It still contributes but less critical, and the model learned what doctors already know. Right? So our model correctly identified that glucose and BMI are the most critical predictors, exactly what medical science says. This means it's learning a real patterns and not just measuring random data. Okay, so for the last objective is using the training data that provided. We have 12 patient sample. Here we have a patient ID, we have pregnancy, glucose, blood pressure, BMI, age, and target. For target is diabetic and non-diabetic. 1 is for the diabetic and 0 is for non-diabetic. So we back to the code here. And we can say I call the uh, file, I call the file path is here. We can say I save the data into the patient sample dataset.csv and call it I call it from there in this using this code. Alright. So we load the patient records and we have, like I said before, we have diabetic and non-diabetic patients. So this is the training data, like example problems the model learned. So it's like 80% for training, which is we teach the model, and 20% for the testing, and we check it if it learned correctly. Data is the foundation for everything else. Without it, we cannot build or test the model. So we test it on new patients. Here we can say I test on the new patient here, which is the 3 pregnancies, and glucose is 160, the blood pressure is 80, BMI is at 35.0, and at age 40. The model predicted diabetic or non-diabetic with high confidence. So I will show you the result here. Alright, so we got this result. This you can see here for step 2, the graph for the step 2. And this is for the step 3 graph. You can see here that there's a difference, a big difference, okay? And the last one is the confidence metric for linear SVM. This one. So we can take 3 keys takeaways, 3 key points that we can see here. Before that, this is the classification report for coefficient matrix, this one. And then we have this one for the step 1. And this a result for the step 2. You can see here. And this for step 3 is verification for the model coefficient. So here is the model coefficient for weights. And the accuracy model is 66.67%. This one is the coefficient matrix interpretations. Here is only classification reports. So here we can see. This one when we add a new patient data that we test just now. So we can see here. So that's all. Okay, the 3 keys that I taught just now. The first one, linear SVM, works well for this problem, and the data is mostly linearly separable, meaning that we can draw a straight line to separate the classes. The second one is feature importance match medical knowledge. Glucose and BMI being the top predictors confirms that our model learn correctly, not just memorizing noise. And the last one is soft margin classification was essential. With C equal to 1.0 that we declare on the coding, we balance having a wide margin versus allowing some errors. Real medical data always has overlaps, which is some healthy people have high glucose and some have diabetics have a normal BMI. So that's all from me for this uh, demonstration for the lab 3. Thank you very much.